Hello everyone, welcome you all to the course UAV design, and in today's lecture we're going to see about length to diameter, fineness ratio and fuselage lofting techniques. The fineness ratio is defined as the ratio between fuselage length and its maximum equivalent diameter. This fineness ratio, it means it talks about, suppose this is the aircraft, it talks about this length of the fuselage, and this is the diameter of the fuselage, this part, diameter of the fuselage. Selecting the correct ratio is a fundamental question of balancing internal volume, weight and aerodynamic drag, right? While designing the fuselage, we have two categories here, subsonic and supersonic. During subsonic optimization, we read from some text which suggests that drag is minimized at a fineness ratio of approximately 3, which is usually assumed as fixed minimum diameter requirement. However, analytical optimization studies show that if volume is held constant, the optimum fineness ratio for subsonic aircraft is between 6 and 8. For most low-speed unmanned aerial vehicles, a ratio between 5 and 10 is generally recommended to ensure sufficient internal volume without creating excessive frontal area drag. Then coming to supersonic class, supersonic optimization. Supersonic drag is typically minimized by a much higher fineness ratio, usually around 14, though it can range from 10 to 15 or more depending on the specific design. Design trade-offs. A very low fineness ratio, for example, L by D equals to 3, that is length to diameter. Length to diameter equals to 3 may fail to provide a long enough tail movement arm requiring the use of extra large tails or a tail boom to maintain stability. Lofting is a mathematical modeling of the aircraft's outside skin to ensure an accurate fit between parts designed and fabricated by different teams. The process ensures that the airframe properly encloses internal components like fuel tanks, engines, while maintaining a smooth aerodynamic contour. Right? This is an spline lofting figure which shows that how these points are drawn, right? And these are the lead ducts, which gives you a brief introduction on how a spline lofting is been done. These points are known points because these are estimated points. We use equations to get these points, and once we get these points are joined using a smooth spline. Conic lofting. It's traditionally a lofting which is done graphically using flexible rulers called splines held by weights, which is called ducts. But it is lacked a unique mathematical definition. In modern traditional lofting, it is based on the conic section, which is ellipse, parabola or hyperbola, which is easy to construct and mathematically it is precise in nature. The shape of the conic depends upon the angle of the cut through the cone. If the cut is perpendicular to the axis of the cone, then the resulting curve will be a circle. If somewhat slanted, then it will be an ellipse. If it is exactly parallel to the opposite side, a parabola is obtained, a parabola curve is obtained, and a greater cut angle yields a hyperbola. Right, this is the conic geometry definition, right, where we have a different cuts here, and then we have the points A, B and C, which are giving us the curves. This is eccentricity here, E is eccentricity in these cases. This is for ellipse, this is for parabola, and this is for hyperbola. Longitudinal control lines. To develop a smooth fuselage points, A start point, B is the end point, and C is the tangent intersection here, and S is the shoulder point, are defined for various cross sections and connected longitudinally. Initially, a line is being drawn from A to this curve BC, and a curve from this a line is being drawn from this point B to this segment AC, which is going through this point S, a short point, right? Both lines will be intersected here, right? And then one more point from C is being drawn here. C is the source here, and it is drawn, and it will be passing over the line which is bisecting CB, this one, and the line which is origin from B, which is bisecting AC here, right? And the line which is sourcing from C and these bisected lines, these are marked. Again, a line from B will be drawn such that it will be passing through this bisected lines on BC, which is passing, which is coming from A, and which is passing from, which is going from B and passing, going to AC, right? So this point is the first point, and same thing is being repeated further so that we get this shape, right? This is the first iteration, second iteration, third iteration, fourth iteration. So we have multiple iterations to get the shape. This is conic layout example. Longitudinal control lines. To create a complete fuselage, the A, B, C and S points of these control cross sections are connected by longitudinal control lines. These lines define the skin of the aircraft. In side view, the A and C lines are often identical because cross sections are typically tangent to the horizontal at the top of the fuselage. See, this is the line A, right? This is the longitudinal control line passing through A, and then we have C. This A and C both will be tangent to each other. It will be identical. Conic shape parameter. The value P is defined as the ratio of distance from the chord midpoint to the shoulder point over the total distance from D to the tangent intersection point. We have equation here, C equals to, that is for C, P equals to ds upon dc. This parameter directly controls the squareness of the curve. A value of P equals to 0.4142 results in a perfect circle, while values near 0.7 create squarer sections, often used to maximize internal volume for landing gear. And more or less, this will be similar to hyperbola. It will be easy to get an hyperbola into squarer sections. Flat trap lofting. A critical cost driver in fabrication is compound curvature, which involves surface curvature in all directions like a ball. Then developable surfaces. A flat wrapped surface curves in only one direction like a cylinder or a cone. It will be like this. It will be only in one direction. Economic advantage. Flat wrapped skins can be cut from flat sheets and bent to shape without expensive stretching or stamping tools. Aerodynamic compromise. While cheaper to build, flat wrapped surfaces are less efficient than smoothly contoured teardrop shapes. These are some advantages of using flat wrap lofting. A flat wrapped surface is defined as a geometry that has curvature in only one direction at any given point, such as a cylinder or a cone. A complex flat wrapped surface allows the cross sections to change shape longitudinally while avoiding compound curvature. This is an example of complex flat wrapped surface. Loft verification and counter guidelines. Buttock plane cuts. To verify smoothness, designers usually vertically slice through the fuselage at exact fixed distances from the center line, and if the resulting longitudinal lines are smooth, the surface will not cause unwanted vortices or premature flow separations. This is the airfoil, which is a butt plane cut of the wing. This is the complete wing from here to here, root to tip, and when it is sliced perpendicularly, it gives the airfoil shape. This is buttock plane cut figure. Closure angles. To prevent boundary layer separations, the aft fuselage deviation from the free stream direction should not exceed 10 to 12 degrees on the top and sides, or 15 degrees on the bottom. So this will be like this, somewhere around. We'll have this angle around 15 degrees. For subsonic UAVs, the rear taper angle should generally be not greater than 20 degrees. Conclusion. Fineness ratio is selection must be balanced, internal volume, structural efficiency and aerodynamic performance. For subsonic unmanned aerial vehicles, a fineness ratio between 5 and 10 is generally optimal, providing adequate internal space without introducing excessive drag. Supersonic designs, however, require higher ratios between 10 to 15 to minimize wave drag, and practical considerations such as tail moment, arm length and component integration must also influence this choice, avoiding extreme values that compare stability or manufacturability. Lofting is a technique which plays a critical role in transition from design to fabrication, while conic lofting ensures precise, aerodynamically smooth contour ideal for performance, and flat wrap lofting offers significant cost advantages for low volume or budget constrained unmanned aerial vehicle. Regardless of the method chosen, loft verification using buttock plane cuts and respecting closure angle guidelines, it's essential to prevent flow separation and ensure aerodynamic integrity. Ultimately, the design of a UAV fuselage is a compromise between aerodynamic efficiency, structural weight, internal volume and manufacturing cost. By carefully selecting an appropriate fineness ratio and applying suitable lofting methods, which is validated through systematic checks, a designer can achieve a balanced airframe which meets both performance objectives and practical constraints. These are the references used for this lecture: Unmanned Aircraft Design, a review of fundamentals by Mohammad H. Sadare; Aircraft Design, a conceptual approach by Daniel P. Raymer; Introduction to Flight by John D. Anderson; and Unmanned Aircraft Systems, UAV Design, Development and Deployment by Reg Austin. Thank you.